Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Clausius integral. The second law of thermodynamics often leads to expressions that involve inequalities. An irreversible heat engine, for example, is less efficient than a reversible one operating between the same thermal energy reservoirs. Another important inequality that has major consequence in thermodynamics is the Clausius inequality. It was first stated by the German physicist R.J.E. Clausius, one of the founders of thermodynamics, and is expressed in 1865 as, that is, the cyclic integral is always less than or equal to 0. This inequality is valid for all cycles, reversible or irreversible. Any heat transfer to or from a system can be considered to consist of differential amounts of heat transfer. Then the cyclic integral can be viewed as the sum of all these differential amounts of heat transfer divided by the temperature and the boundary. 1. Clausius inequality can be derived based on Carnot principles. A reversible cycle, as shown in the PV diagram, can be divided into many cycles with the isentropic path lines. All the cycles are reversible, and each one undergoes the Carnot cycle. Based on Carnot principles, we have, that is, the cyclic integral of delta Q over T for a reversible cycle is equal to 0. An irreversible cycle, as shown in the PV diagram, can be divided into many A, B, C, D cycles with the isentropic process. Not all the ABCD-like cycles are reversible. Based on Carnot principles, we have, that is, the cyclic integral for an irreversible cycle is always less than 0. We then conclude that for all the cycles, the cyclic integral is always less than or equal to 0. This is the Clausius inequality. This indicates the cyclic integral is 0 for any reversible cycle. It is negative for any irreversible cycle, and it is positive for any impossible cycle. Note 1. Tr is the temperature and the boundary. 2. For the working fluid in the cycle, the positive sign is determined by the heat addition of working fluid. 2. Clausius inequality can also be derived from the Kelvin-Planck statement of the second law. Consider a system connected to a thermal energy reservoir at a constant thermodynamic temperature through a reversible cyclic device. The cyclic device receives heat from the reservoir and supplies heat to the system whose temperature at that part of the boundary is T while producing work. The system produces work and the result of this heat transfer. Applying the energy balance to the combined system identified by dashed lines yields. Delta WC is the total work of the combined system, and DEC is the change in the total energy of the combined system. Considering that the cyclic device is a reversible one, we have eliminating delta QR from the two preceding relations yields. Let the system undergo a cycle while the cyclic device undergoes an integral number of cycles. The preceding relation becomes. It appears that the combined system is exchanging heat with a single thermal energy reservoir while involving work WC during a cycle. On the basis of the Kelvin-Planck statement of the second law, which states that no system can produce a net amount of work while operating in a cycle and exchanging heat with a single thermal energy reservoir, we reason that WC cannot be a work output, and thus it cannot be a positive quantity. We then have, considering that TR is the thermodynamic temperature and thus a positive quantity, we must have the Clausius inequality. This inequality is valid for all thermodynamic cycles, reversible or irreversible, including the refrigeration cycles. If low irreversibility occurs within the system as well as the reversible cyclic device, then the cycle undergone by the combined system is internally reversible. As such, it can be reversed. In the reversed cycle case, all the quantities have the same magnitude but the opposite sign. Therefore, the work, which could not be a positive quantity in the regular case, cannot be a negative quantity in the reversed case. Then it follows that the work is zero, since it cannot be a positive or negative quantity. Therefore, conclusion, the equality in the Clausius inequality holds for totally or just internally reversible cycles, and the inequality for the irreversible ones. 3. Can also be derived based on the entropy equation. Please try it by yourself. There are two effects of the Clausius integral. One determines whether the cycle or the process performed in a closed system is reversible and possible, so as to link the internal characteristics of the cycle and the impact of the cycle on the surrounding. 2. The quotient of heat and temperature is equal to calculate the entropy change of the irreversible process. Okay, that's all for this task. Thank you very much, and see you next time.